Section 3.4, Sensitive Information Disclosure, How Private Data Leaks Through LLM Applications. This is OWASP LLM 02 2025. It jumped from number 6 to number 2 on the OWASP Top 10 for LLM applications between the 2023 and 2025 editions, the largest single ranking leap of any category. This rise reflects both the rapid growth of LLM-powered products and the accumulation of documented incidents where private data was exposed through AI systems. Sensitive information disclosure in LLM applications has two distinct mechanisms that require completely different defenses. The first is context window data leakage. This is when the model returns data from its context window that belongs to one session or user and exposes it to a user who was never meant to see it. This is an application architecture problem. The second mechanism is training data memorization. The model reproduces text it was trained on, which may include personally identifiable information, proprietary code, or copyrighted content. This is a fundamental property of how large language models work. Understanding the difference matters because the causes and defenses are entirely different. Let's start with mechanism 1, context window data leakage. Every response an LLM produces is a function of its context window. Context leakage occurs when data intended for one user ends up in another user's context. There are three failure modes. First, shared memory without per-user isolation. If conversation history is stored in a shared store indexed only by a username string, a logic error or injection attack can expose one user's history to another. Second, shared RAG retrieval without access controls. If the retrieval layer doesn't enforce per-user permissions, a query can trigger retrieval of another user's private documents. Third, shared inference caches. If key-value caches are not scoped to individual users, a cached result from one session can be served to a different user. This is not hypothetical. In March 2023, a bug in OpenAI's Redis client library caused ChatGPT to expose fragments of other users' chat histories to the wrong users. During a 9-hour window, approximately 1.2% of ChatGPT Plus users could see titles and first messages of other users' conversations, along with limited billing information, names, email addresses, and last 4 digits of credit card numbers. The root cause was a race condition in Redis connection pooling. Cached data from one user's request was served to a different user's session. The lesson: anywhere you cache or store user-specific context and serve it in subsequent requests, a boundary failure will leak private data. The Samsung incidents in April 2023 illustrate context leakage in the other direction. Sensitive data entering an LLM's context and leaving through the provider's infrastructure. Within a single month, 3 Samsung semiconductor engineers pasted confidential data into ChatGPT. One pasted proprietary source code to find a bug. Another pasted internal code for optimization suggestions. A third pasted transcripts of internal meetings. According to Lasso Security, 13% of all enterprise generative AI prompts contain sensitive organizational data. Samsung responded by banning all generative AI tools company-wide and capping prompt lengths at 1,024 bytes. This shows that context leakage is also a user behavior problem. Developers need to design both architecture and user experience to minimize how much sensitive data enters the model context. Let's look at a vulnerable code pattern. In this example, the build context function takes a username string and fetches all memory for that user. The problem: memory is fetched by a user-supplied username with no additional isolation. If the username is wrong due to a bug or injection attack, the function retrieves another user's conversation history and injects it into the context. Once that data is in the context window, the model will freely reference and quote from it. It has no mechanism to recognize that it belongs to a different user. The impact is severe. Private conversations, medical questions, and financial details get exposed to the wrong user. Here's the secure pattern with 3 key elements. First, namespace all memory keys by a verified server-side user ID, never a user-supplied string. The memory key uses the authenticated user ID from the server, preventing cross-user key collision. Second, limit history. Only load the last n turns to reduce the exposure window. Third, redact PII before storing. The store turn function runs messages through a redaction pipeline that removes emails, phone numbers, and social security numbers before they are persisted. Even if memory is leaked, stored history contains less sensitive data. These three defenses work together. Isolation prevents the bug, limiting reduces the blast radius, and redaction reduces sensitivity. Now, mechanism 2, training data memorization. LLMs compress patterns from billions of documents into their weights during training. This compression is imperfect. Sequences that appear repeatedly can be reproduced nearly word for word when prompted correctly. In 2021, Carlini and colleagues demonstrated the first practical extraction attack on GPT-2. They extracted hundreds of verbatim sequences, including real names, phone numbers, email addresses, and code snippets. Larger models were consistently more vulnerable. In 2023, the same team extended this to ChatGPT. Using a divergence attack, prompting the model to repeat a single word indefinitely, ChatGPT output raw training data at 150 times the normal rate. Using approximately $200 in API calls, they extracted several megabytes of PII from the model. The key insight: sequences that appear repeatedly, are long, or follow distinctive patterns like a name paired with a phone number have significantly higher memorization probability. Here are the concrete memorization rates from research. GPT-J memorized at least 1% of its training set. StarCoder memorized at least 8% of sampled training examples. Email addresses could be extracted from GPT-J correctly 16% of the time. Most alarming is the fine-tuning amplification effect. Fine-tuning on repeated sensitive data raises memorization from a baseline of 0 to 5% up to 60 to 75%. That is a 64% average increase. If you fine-tune on internal data containing PII, the model may reproduce fragments to any user who asks the right questions. What gets memorized includes full names with addresses and phone numbers, email addresses, verbatim book passages, source code with unique identifiers, and even UUIDs and cryptographic keys. Let's break down the risk by data type. User PII has medium memorization risk, but high context leakage risk, with the primary concern being cross-user leakage. Health and medical data has low memorization risk, but high context leakage risk, creating HIPAA exposure. Internal source code has high risk on both fronts, as seen in the Samsung incidents. API keys and credentials have very high context leakage risk if stored in system prompts, with the concern being direct exploitation. Proprietary business documents carry high risk on both fronts if used in fine-tuning or RAG. And copyrighted content has high memorization risk with legal exposure from verbatim reproduction. The key takeaway is that different data types face different threat profiles, and your defenses need to address both memorization and context leakage paths. The most actionable memorization risk for developers is fine-tuning. When you fine-tune on proprietary data, you teach the model to produce text resembling your internal documents, making it more likely to reproduce fragments verbatim. This is especially dangerous when the fine-tuning data contains customer records with names and account numbers, legal documents with privileged content, employee data and compensation information, or internal security documentation like network diagrams and vulnerability reports. The mitigation is not to avoid fine-tuning, but to treat fine-tuning data with the same access controls you apply to the data itself. Scrub PII before it enters any training pipeline using tools like Presidio or commercial DLP services. A critical defense layer is PII output filtering. On the left, the vulnerable pattern, the model response is returned directly with no output scanning. Any PII from memorization or context leakage goes straight to the client. On the right, the secure pattern. Before returning the response, we run it through a scan and redact function that checks for email addresses, phone numbers, social security numbers, and credit card numbers. Detected PII is redacted before delivery, and the detection is logged as a security event. Importantly, we never log the raw content containing the PII. This output filtering layer is essential because it defends against both training data memorization and context window leakage simultaneously. No matter how PII ended up in the model's output, this layer catches it before it reaches the user. One of the most common ways sensitive data accumulates silently is through application logging. A typical AI application logs user input messages, which may contain PII, model outputs, which may contain PII from memorization or leakage, and the full context, which may contain retrieved documents with PII. Over months, these logs become a concentrated archive of sensitive information, stored in cloud logging services, accessible to engineers with log read permissions, and retained for 90 or more days. A single compromised account can expose every user's data. The rules for logging AI applications: log user IDs and session IDs, not message content. Log tool call names and success or failure, not full parameters. Log PII scanned and redacted versions of outputs, and never log the full context window. Now, the practical defenses for context window leakage. These are primarily architectural. First, per user context isolation. Namespace all memory store keys with a verified server-side user ID. Apply access control checks at the RAG retrieval layer. Never share inference caches across users. Second, minimize what enters the context. Retrieve only what is necessary, such as the top 3 documents rather than the entire knowledge base. Load only recent conversation history. Use anonymized or tokenized identifiers instead of real names where possible. Third, PII scanning on outputs before logging. Scan AI responses for PII patterns before writing to application logs, preventing PII from accumulating in log files accessible to many engineers. Here is the complete defense summary. For context window leakage, namespace all memory and cache by verified server-side user ID. Apply access controls at the RAG retrieval layer, minimize data entering context, and scan outputs for PII before logging. For training data memorization, scrub PII from fine-tuning data with tools like Presidio. Deduplicate training data, reducing memorization by approximately 10 times. Apply output PII filters in production, and use anonymized identifiers where possible. For PII in logs, log only user IDs, not message content. Log tool call names, not full parameters. Apply PII scanning before writing logs, and never log the full context window. Remember, treat AI context as a data boundary. Namespace by user ID, scrub training data, scan outputs for PII, and never log raw message content. In the next section, Section 3.5, will cover denial of wallet, where attackers target your billing account instead of your data. For more details, visit wisebuilder.dev.